The focus for our video today is in class 10. This is the part of standard 3. We're going to be focusing on two special types of triangles today. Isosceles and equilateral triangles are the main focus. So there is an introduction section. So thinking back to yesterday's notes, our goal is to classify each of the triangles that we've been given by angles. So go ahead and pause the video, give that a try. Meet me back here once you have answers, and we will see how you did. Welcome back. Remember, when we're classifying by angles, we have 4 choices. A triangle can be acute, equiangular, right, or obtuse. So when we investigate the first triangle scenario, the goal would be to find that missing angle, the measure of angle D. We can do that using the triangle sum theorem. All 3 interior angles have to add to 180. So that turns out to be 118 degrees, which is more than 90, so that would be an obtuse triangle. For example 2, they're showing us that all of the angles match. They're all x, which means they're all equal. If we were to solve, we could take 180 and divide it by 3 to figure out that x is equal to 60 degrees. That means our triangle is equiangular because they're all the same. For example 3, we see a right angle marked with that box. We don't know anything about the other angles, but that's okay. As soon as we see one right angle, that means we have a right triangle. And last but not least, we've got a little algebra equation to solve for this last one. The angles are all 3 mysteries, but we know since they're on the inside of a triangle, they have to add to be 180. Once we track down x, we can plug that back in to find the individual angle measures. And since all 3 measures are less than 90, that would be an acute triangle. So some vocabulary review from yesterday. Moving into the new material, we're going to look at what happens when a triangle has some congruent parts. As a reminder, the word congruent could be symbolized with an equal sign with a squiggle on the top, and that means that things are the same size and the same shape. So when we look at this first example, it says that this is an isosceles triangle, and what we notice is marked as congruent would be side EF and side FG. Those 2 segments are marked with ticks, and so we know they're congruent to each other. If we look at example B, that's an equilateral triangle, our second new vocabulary word for today, and we notice that all 3 of the sides of this triangle are marked with those ticks. So all 3 of them are congruent and have exactly the same measure. We've already talked about equiangular a little bit, so this third example is showing us an equiangular triangle. That's showing us that all 3 of these angles are equal to each other, all congruent. And so what happens with triangles is that equal sides are going to give us information actually about equal angles as well. If we travel across the triangle from a congruent side, we're going to make our way to what we call the opposite angle. And if these 2 sides are congruent, then when we travel to these 2 opposite angles, they will also be congruent. So when sides have the same size, the angles across from them have the same size. So if we do the same thing with our equilateral triangle, we're going to travel across from all 3 sides, which means we're going to end up with all 3 angles as being congruent. And then on the flip side, if we start with the angles congruent, we can travel across to the opposite side and mark that those sides are going to match as well. So when we have congruent information in a triangle, it's kind of like a 2-for-1 situation. If we have congruent angles, we can find some congruent sides. If we have some congruent sides, we can find some congruent angles. And those are the ideas that are going to help us to solve problems. So if we move to the next section, important vocabulary and theorems, we're going to kind of formalize those ideas, sorry for the slantiness there, and give them some names. So the first idea that we're going to talk about in terms of formalizing what we just did up above is the base angle theorem. The base angle theorem tells us that if a triangle is isosceles, In other words, it has these two congruent sides. Then the angles opposite the congruent sides are also congruent. So this is the isosceles fact that we start with. And then what we end up with is not only the isosceles fact marked, the two congruent sides, but also if we travel across, we're going to get to two angles that have matching measurements as well. The next idea is called the converse of the base angles theorem, which just means that we flip the two parts of that sentence. So we're going to start with a triangle that has two congruent angles. We can see that pictured right here. So we start with those angles. And then what we're able to say as a result is that the sides opposite those angles are congruent. So we'll start at this angle and travel across. That would take us to this side. Then we'll start at this angle and travel across, and that would take us to that side. So that idea works in both ways. If we start with the sides, we can find some congruent angles. If we start with some congruent angles, we can find some congruent sides. And then we have what's called a corollary of the base angles theorem. That's an idea that's related to the base angles theorem. This related idea starts by showing us three sides that match. So we called that earlier today equilateral. That was one of our new vocabulary words up top in our ABC examples. So if a triangle is equilateral, then we know that we can travel across from those congruent sides and make it to three congruent angles. And we had a word yesterday for a triangle that has three congruent angles. We called it equiangular. So basically, if we have an equilateral triangle, then we also know we have an equiangular triangle. If we flip that idea backwards and talk about the converse of that corollary, if we start with the angle information, that means we start by knowing that a triangle is equiangular. Then we're going to be able to mark those congruent sides opposite of each angle, and we will also be able to classify it as being equilateral. Now, we're not going to ask you to memorize the names of these things quite yet. Some of them will show up in a later standard when we start doing proofs, but for right now, the idea is that you need to understand them and solve problems with them. So don't worry too much about memorizing those phrases right now. Focus on the ideas and what's true. All right, the second phase of today is to continue our classifying. So yesterday, or in our previous notes, we classified triangles based on angles. Today, we're adding some more vocabulary words that will help us classify triangles based on sides. And we've already used two of these vocabulary words today. So isosceles and equilateral have already popped up. Isosceles was a triangle with two congruent sides, and equilateral was a triangle with three or all congruent sides. Scalene is the new one, and that's going to be a triangle that has no or zero congruent sides. So basically, all three sides are unique. They're all different. So they're asking us to go back now to the beginning in the introduction section and classify the triangles up there based on their sides if we have enough information to do so. So if we go back to these examples at the top, we're going to need to look carefully because all we have are angle clues. But when I investigate the angles in this first triangle, I'm noticing there are two angles that match. So if we use our converse of base angles theorem down below, that means that the sides opposite those angles, so DF and then DE, would also need to match. So that obtuse triangle could also be classified as an isosceles triangle if we were classifying based on sides. For example 2, all three of our angles matched. So now we know that that forces all three of our sides to match as well. So it's equiangular when we talk about classifying based on angles, and it would be equilateral when we talk about classifying based on sides. Number 3 is tricky. We only know one angle of this triangle, so we do not have enough information to classify this one based on sides because we don't know if these other angles match or if they're different. If these match and both are 45 degrees, then this would be an isosceles triangle. But if these are different, then all 3 sides would be different and we would call it scalene. So that one we're not able to classify based on sides. We don't have enough information. But example 4, last example, all 3 angles are different. That means that all 3 sides are also different. So this one would be an example, the first one we've seen so far today, of a scalene triangle, where all 3 sides have their own unique measurements. All right, that's it for the front side, so go ahead and flip to the back and meet me there for some examples. I think you could probably tackle these first 3 examples on your own, so if you're ready for that challenge, go ahead and pause the video and give them a try, and then press play when you're ready to see how you did. If you feel like you're still a little bit confused, then just keep watching. Okay, for this first example, we have 3 tasks. Find the measure of angle A, classify the triangle by angles, and classify the triangle by sides. I can already tell that we're going to be able to classify by angles and sides very quickly. I see an angle that's larger than 90, and I see 2 congruent sides. So without even finding out any other angle measures, I know that this triangle is going to be obtuse based on its angles, because that 118 is bigger than 90. And then because it has 2 congruent sides, I can tell that this is going to be an isosceles triangle based on its sides. That isosceles fact is also going to help me to find angle A. Angle A is missing, but so is angle C. So without having 2 out of the 3 angles, it's very difficult for me to use the triangle sum theorem. So I need to remember that across from these congruent sides are going to be some congruent angles. So angle A and angle C are not different. They're actually the same. So since there aren't any variables in this picture, I could put an X in both of these locations to help me out, if that helps you. Then it would be that X plus 118 would give me my total triangle sum of 180 degrees. There's also a way to think about that with just arithmetic. Some people's instinct is to subtract the 118 away from 180 and then divide those leftover degrees by 2. That's absolutely fine. But if you're more of an algebra person, we have 2 mystery angles that together are going to be 62 degrees. And so when we divide that by 2, each one of them individually is going to be 31 degrees. So the measure of angle A is 31 and the measure of angle C would match. Moving into example 2, I feel like we have enough to classify by sides right away because I see tick marks on all 3 sides. Our new word for that is equilateral. But thanks to those corollaries we talked about, or the converse of the corollary, if those sides match, those angles also match. So that means that this triangle is also equiangular. Those 2 equa words always go together. So if a triangle is equiangular, it's equilateral, and vice versa. Now that means that all 3 of these angles match. And anytime all 3 of the angles match, we automatically know that each one of them has to be 60 degrees. 60 plus 60 plus 60 is 180. So the easiest way to solve for x would be to set that 6x squared angle equal to 60, because we know that's its measure. You could also add 3 of those 6x squareds together and add it up to be 180. You'll get the same exact answer. This one does have a square, so we're going to need to square root, and the square root of 10 is not a super friendly number, so we're just going to leave that as plus or minus the square root of 10. It's positive or negative square root of 10. Both of those will give you the same answer if you plug them in because you're squaring right away, which takes care of that negative. So both of those are acceptable geometry answers in addition to being acceptable algebra answers. All right, last example at the top here. I see two congruent sides. So that should tell me that by the sides, this would be an isosceles triangle again. I can't quite tell based on angles because these angles are mysteries to me. So I do know, though, that across from these congruent sides, I should have some congruent angles. Without filling in that angle, I'm going to be a little bit stuck because I don't have the 3 inside. So if I want to be able to use 180, the best thing to do is to notice that angle A is 3x plus 5, which means angle C could also be labeled as 3x plus 5. Now that we've got all 3 interior angles, we can add them all together, and that total will be 180 degrees. Collecting all of those x's together will give us 8x total. Collecting those positive 5's together give us positive 10. Subtract the 10 from both sides and do some division. We end up with 21.25. That's an exact decimal if you write both the 2 and the 5 down, so just keep it nice and exact. To finish this one out, we're going to need to plug it in. They want to know the measure of angle C, so we might as well start there. 3 times 21.25, plus 5 will give me the measure of angle C. So take that 21.25 and multiply it by 3 first and add 5 to it. So angle C turns out to be 68.75 degrees. Angle A would be the same, 68.75 degrees. And then angle B, I'm going to go ahead and figure that one out too. 2 times 21.25. 2 times 21.25 is 42.5 degrees. And the reason I did that is to classify by angles, I really want to see all of them. If the first 2 are acute, I want to check out that third one to see whether it's going to be acute or something different. It turned out to be less than 90. So with all 3 angles being acute, this is officially an acute triangle. All right, on to example 4. This one doesn't have any algebra in it, but it is asking us to come up with a couple different angle measures, angle 1, angle 2, and angle 3's measure. And we only have one value to use to get us started, but we do have some congruent marks. So I'm going to start with this triangle over here because that's the one where the 68 is at. And I'm going to think about why these congruent marks might be here. If we travel across from those congruent sides, we should land on congruent angles. So that 68 actually also gives me the measure of this angle up top, which is good news because if I know both of those are 68, I can now find the measure of angle 1. All 3 of those would add together to be 180. So if we do 180 minus those 2 68s, we should be able to say that the measure of angle 1 is 44 degrees. Right there, 44 degrees. Now, I see something from standard 2 right here in the middle. Do you notice that X shape? Angles across from each other in the X. See if you can remember what those are called. Those are those vertical angles we learned about. So they are supposed to be congruent, which means that angle 2 is also 44 degrees. And then we've made our way into this triangle over here on the right side of the picture, where we have another set of congruent sides. So this time around, across from the congruent sides is blank in both cases. So 44 is the angle that's different from the others. But if I have those 2 angles as mysteries, we know they're going to match because they're across from congruent sides. So basically I could call them both angle 3, subtract away that 44 degrees that's already used for that top angle and then divide those leftovers by 2 to figure out what the measure of angle 3 is equal to. It turns out to be 68 degrees. Now, some of you might have said 68 degrees because you're noticing in this triangle, if the two angles match and that one's 44, the same thing has to happen over here. If that angle's 44 and these two match, there's no other option but for them to be 68. So you could solve it based on algebra and the triangle sum theorem, or you could use some logical thinking there to figure out what the measure of angle 3 is equal to. Example 5 is up next. I'm going to start on the part of the picture where I actually have a measurement given to me, which is that 64 degree angle at the top. A similar thing happens to what we just did over here. This angle is going to be congruent to this angle because they're across from those equal sides, those congruent sides. So angle 1 is actually showing up twice in that triangle. So the measure 2 of those angle 1s plus 64 would combine to be 180. Or if your brain is okay, going straight for the subtraction and then dividing those leftover angles by 2, it's okay to do that without writing out all of the algebra equation stuff. Algebra is just here to help you with these problems if you need it. So this time around, we've got 58 degrees as the measure of angle 1. If we're thinking about how to move into the next part of the problem, I'm noticing something else from standard 2 right here. I just figured out that this angle is 58. Kind of ignore the rest of this picture here. What do you notice right here between that 58 degree angle and that angle 2? Hopefully you're thinking linear pair theorem back from our previous work with angles. So if I take 180 and subtract that 58 away, angle 2 should be the result. So 180 minus that 58 is going to give me 122 degrees for the measure of angle 2. Angle 2 is technically also an exterior angle for this original triangle, so you could have found the measure of angle 2 by adding up those two non-adjacent interiors. 64 plus 58 will also give you 122 degrees. Last but not least, if we turn our attention to this triangle over here, we still have two congruent sides. So across from those congruent sides are going to be another set of congruent angles. But this time around, 122 plus 2 of those angle 3s will take us to our total of 180 degrees. So the same idea, we're going to do 180 minus that angle that we have, and then we're going to divide that in half to figure out what just one of those two missing angles is equal to instead of both. Looks like 29 degrees will be the result. Okay, 4 problems left. Lots of examples to go along with these two ideas because they can show up in lots of different ways. When I look at example 6, I'm noticing right away that we have an exterior angle. And so I'm remembering that I can find the measure of an exterior angle by adding up the two non-adjacent. So this one doesn't matter, but these two do. So 42 is one of my non-adjacent interior angles, but I'm missing the other one. It would be right here. I also notice I've got two congruent sides. So even though all I care about is finding this one, it's also good for me to remember that these two angles match. So doing some work off to the side, 180, the interior sum, would come from 42 plus those two question mark angles. So similar to the previous one, I'm going to do 180 minus that angle that I had, which would be 138, and then divide by 2 to figure out what that question mark angle is. And that angle turns out to be 69 degrees. So I can fill out the rest of my exterior angle theorem. 42 plus 69 gives me 111 as the value for this exterior angle. So now I can switch into algebra mode, subtract 21 from both sides, and then divide by 10 to give us our value for x. You could have also figured out what this question mark angle is, 69, and used your linear pair theorem. 69 plus 10x plus 21 would be 180 degrees. So I used exterior angle theorem just because it was new and I wanted to give you a chance to see it again, but you could also use your linear pair theorem to finish out that problem. Okay, example 7. I am noticing that I have a number over in this triangle, but I don't have any other clues about congruent sides or congruent angles. So without some more information, I don't feel like that 81 degrees is going to be very helpful. So I'm going to focus over here to begin with, because I notice I've got 2 angle measures, but also 2 congruent marks. So if I travel across from those congruent sides, it ends up being that these 2 angles have to be congruent as well. So my 30 plus 6x has to equal this negative 42 plus 24x. I'm going to choose to subtract 6x from both sides because I like to keep my x values positive. So that'll give me 18 x's left over. Adding 42 over will give me a total of 72. And then 72 divided by 18 tells me that my x value is equal to 4. Now, typically, once we find something, it's helpful when we are looking for our next task. Like up here, when I found angle 1, that angle 1 helped me find 2, and then that angle 2 helped me find 3. So I think it would probably be best for us if we took this 4 and we plugged it in. 30 plus 6 times 4 tells us that this angle is actually 54 degrees. If we did the same thing here, we should get the same result because those were supposed to be congruent angles. And so I feel like we can find this angle right here now because we have 54 plus 54 plus that equal to 180. Sorry for the bell ringing. Finishing up that subtraction, we're going to end up with 72 degrees for that angle right there. And then like we saw in example 4, these are vertical angles, so they should match, which means 72 degrees can also be used in that triangle over here on the right side of the picture. So now that we know 2 out of those 3 angles, we can use our triangle sum theorem to figure out what that value for y is. So 180 minus 72 minus 81 gives us a leftover 27 degrees for y. Example 8 looks very similar to example 5, except I notice that there's algebra involved. So if we focus in on these 2 congruent sides, we can travel across and we should find 2 congruent angles. So even though these look different, they need to be equal. So an equation would be 24 plus 5y equals 10y minus 16. I'm going to subtract 5y for my variables to be on the right side, add 16 for the numbers to be on the left, and then 8 will turn out to be my value for y. Looking at x, it's in the other triangle, which I don't know a whole lot about, except that there are 2 equal sides, so this angle would also be equal to x. Without knowing this angle here, though, we're going to be stuck. So I think the best course of action is going to be to take this 8 and plug it into this angle right next door. 10 times 8 is 80, and 80 minus 16 is going to give us 64 degrees for this angle right here. And then just like in example 5, we've got a linear pair sitting here. So if that angle is 64, we can do 180 minus 64 to fill in the other part of that linear pair. Now we've got all 3 angles labeled in the interior of that triangle on the right side of the picture, so we know they need to add up to be 180 degrees. So 2x is going to equal 64, and x turns out to be 32. So kind of an algebra version of example 5 where we did that all but with numbers. Last but not least, this doesn't really seem like it belongs on today's notes because I don't see any congruent sides and I don't notice any congruent angles, but I do notice that I have all 3 interior angles. So I'm going to add all 3 of those angles together to be equal to 180 thanks to my triangle sum theorem. And then I notice I'm in quadratic equation mode where I have x squareds and x's. So I'm going to need to subtract 180 and make that equation equal to 0. 90 minus 180 is negative 90. And then we're going to need to go through the factoring process for this one to figure out what these factors are equal to in order to solve. We're looking for things that multiply to be negative 90. So 2 numbers need to multiply to be negative 90. And those same 2 numbers need to add to be positive 9. So if we start thinking about things that multiply to be 90, I don't think that 1 or 2 or 3 is going to work. 90 divided by 4 gives me a decimal. 90 divided by 5 is 18, so those won't make 9. 90 divided by 6 is 15, so that's going to work. If I make the 6 negative but the 15 positive, they'll multiply to be negative 90. But then they will also add to be positive 9. So x minus 6 and x plus 15 will be my 2 binomials. So if I set those 2 parts equal to 0 real quick, and I solve, sorry for the bell again, we're going to end up with x equals 6 and x equals negative 15 as our algebraic answers. Thinking about plugging those back in, though, 9 times negative 15 is going to be a problem because that means this angle would have a negative angle measure, so that one's not going to work in geometry world. If we take the 6 and we plug it in, that would be 54 degrees, and then 6 squared would be 36 degrees. That all seems acceptable. So x equals 6 will be the only answer that we'll give for our geometry problem. Thanks for watching today. I know this one was a little longer than usual, but we'll see you back in class.